and I'll be your presenter today. Just want to make sure that I take care of some housekeeping stuff. Um, all of you are currently muted and you won't have access to the microphone, but you can use the chat window on your left hand side of the screen to send messages to us. I'm also here joined by Pedro and Carlo, both from Gold Roll Technologies, and they will be monitoring the chat channels, basically the Q&A, and you can type in your questions or comments there. We will also be having some polls during this presentation, just to get an idea about who you are and what kind of function that you do at your institution. So I do have one right now which is asking about what market do you belong to, or what industry that you belong to. So if you have a chance, feel free to answer those poll questions. These will be really helpful for us as we go along. And I'm going to wait a little bit more time to give some more people some time to join, but we should be starting in about a couple of minutes. Okay, um, let's go ahead and get started. Um, once again, thank you for attending this webinar. This is going to mainly focus on web guiding applications and um, a few advanced web guiding concepts. Basically, we're going to deal with edge guiding and line guiding. We're not going to cover any control concepts in this presentation, but more in terms of structurally, how do you do edge guiding for different kinds of application. So the key concepts that we will be covering in this edge guiding aspect of it is single edge guiding, that is guide the web based on just one edge. And then what is center guiding? And we'll also cover some topics about sensor positioners. There are different types of sensor positioners. What is a moving sensor center guiding system? Um, some of the later concepts or the current technology is related to what is called as a guide point. So we will talk. Okay, so there are some feedback saying that they're not able to hear. One second. Okay, so hopefully you guys are able to hear me. Joe, if you can hear me, just say yes. Okay, so the current technology with respect to guiding involves a concept called as guide point. We'll talk a little bit about guide point, and then we'll also talk a little bit about remote guide point adjustments. This is needed for coordination between different web guides. And then we'll also talk about a couple of different concepts called as deadband and edge filtering. So that's kind of the quick overview of what we're going to look at in edge guiding. We're also going to look at other things related to line guiding, as well as what are some of the issues with both of these techniques. Okay. Okay, so in terms of edge guiding, most of you are familiar with this. We have a web guide, and an edge sensor is there to provide the feedback for the web guide mechanism. Last month, we talked about the guiding principles and fundamentals of it. But essentially, in most machines, in edge guiding kind of an application, you position the sensor either on the operator side or on the drive side, drive or the gear side. And then the web is guided to the middle of the sensor position. And then the sensor is positioned in a location along the cross machine direction, so that the alignment provides the required justification of the web. So the main thing with this kind of a system is that it works well for most cases, and for maybe majority of the applications, there's no issue with it. The main issue comes in when we have to change the web width. Whenever there is a product changeover and you do a web width change, then the sensor has to be repositioned. So as we get narrower and narrower, the sensor has to be moved. It has to be located at a different location there. And that location of the sensor has to be justified based on the process requirement. So in these examples, the sensors were moved so that the web centerline position is always the same irrespective of the web width. But in certain other applications, it may not be necessary, and it may be necessary to justify along the operator side or maybe along the drive side. So that is the only thing that someone has to do in terms of whenever they do a product changeover, is to move the sensor. But moving the sensor creates opportunities for operator errors, and this can have other consequences with the web guiding performance. Now, in order to, another way of doing the guiding is to have two sensors, one on either side of the web. This is called as center guiding, and the center guiding is one of the commonly used techniques whenever we need to justify the web to the middle of the machine or the middle of the process. Here, in this case, the control system takes the values from the two sensors, and the average of those two values will provide the centerline position. And then the web will be aligned to the middle of the two sensors. That's what happens in center guiding. Again, when we have center guiding, we still have the same problem with web width changes, and this requires the sensor to be positioned on either edge. And here it's a little bit more complicated in the sense that when you move both these sensors have to be moved equidistant from the centerline position of the machine. So again, creates opportunities for operator error during changeover and things like that. In order to avoid the issues with manual positioning, and also to automate the process, some kind of a mechanism are used to position the sensor. These are called as sensor positioners. As you can see here, this is basically an actuator that drives some kind of a lead screw or a belt or anything like that. And then the two sensors are mounted on that linear rail or lead screw mechanism. And Um, when the web width needs to be changed, this actuator is driven so that either it retracts or it goes towards the web, or it goes away from the web, inside the web or outside the web, to uh, move the sensor to the right location. Now, this control can actually be done continuously. It doesn't have to happen only when a machine is stopped or when a product changeover occurs. The way it is done, if it's done continuously, is to actually have another control loop where the two sensors are actually chasing the web. One control loop is used to guide the web where it's actually guiding, and then the other control loop is used to chase the web so that it can adapt for the web width changes. So this is usually referred to as moving sensor center guide. The actuator can be electromechanical, or it could also be hydraulic. Um, but most commonly it's electromechanical actuators are those that are used right now. So an automatic sensor positioner is used to move the sensors so that um, the web width changes are being accommodated um, by this system. Now, the main issue with sensor positioners or moving sensor center guide is mechanical wear and tear. As you can imagine, the actuator needs to continuously move back and forth, and then that creates a lot of issues. It is also complicated just because of the fact that you have two control loops and there are two control gains that someone needs to worry about. One is for the guide mechanism, and then the other is for the chasing mechanism. Um, and then obviously this requires an additional drive or an additional output, an actuator for the system. And then all of these just makes it complicated. There are also issues with it in terms of stability issues if the chasing is too fast and things like that, that are plaguing this kind of system. Um, Again, when the web width changes, the sensors are moved back and forth, and this can happen automatically, continuously, or it can happen during changeovers where the operator press the button to chase the web and then stop the chasing mechanism and continue guiding the web. An alternative solution, which is getting more popular lately, is actually to use two sensors, two wide sensors that can actually span the entire web width change. When we do something like this, where irrespective of the web width, you don't have to move the sensor, then this kind of a mechanism completely eliminates mechanical moving parts, reduces wear and tear on the system, and then it will be simple to use. There will be no need for the sensor to be moved, and it's easy to maintain. And there's only one actuator. The only one actuator is the actuator on the web guide, and hence there's only one loop. Again, the two sensors will provide their own measurements, and then the control system will use the average of those two measurements. And if the sensors are wide enough so that it can capture the entire width change that is experienced in the process, then this would be a really simple system to use. It doesn't have to be two sensors. If the sensor is wide enough, it can actually cover the entire entire web surface so that it can look at both the edges of the web. Again, like I said, this is one of the most robust and simple kind of installation where it reduces operator errors and things like that. Now, one of the things that when we have a wide sensor that comes to us is what is called as a guide point. So here we have the sensor window, and this might have a sensor range from maybe 2 inches to maybe 37 inches. It could be any within that range. And the old sensors were like mainly like point source sensors, and they were just looking for the edge position, and it was just looking at just a small variation. And as long as you're doing a guiding, the sensor range really doesn't matter. So we were able to get away with a smaller sensor range. But with the advances in sensing technology and things like that, now we have the opportunity to look at a wider, excuse me. So with a wider sensor window, now we have the opportunity to not only guide the web to the middle of the window, but to any arbitrary position within the window. The reference position, or where the web guide is controlling the web location, that's called the guide point. And then the error, if the web position falls to the left here, it'll be a positive error. And if the web position falls to the right here, it'll be a negative error. And we can actually electronically move the guide point um, in such a way that if the web width changes, we can actually move the guide point instead of moving the sensor. Now this is an example where the web width reduced, so we moved the guide point. And this allows us to, instead of manually positioning the sensor, we can electronically position the location of the web. So by moving the guide point, you can actually use a single sensor, and you can still do center guiding as long as you know how wide your web is, and it's just a matter of mathematics to get it there. Electronic guide point enables us to do quick changeover. It doesn't require an operator to move the sensor manually or through the sensor positioner. Manual movement of the sensor are being avoided right now just because of the safety reasons and things like that. We don't want operators to get into the machine and move the sensor. So there are some lead screws or motorized stages that would move the sensor. And then if we know the width of the product based on a product code or something like that, then we can pre-program this guide point changes whenever a changeover occurs. And this makes it extremely simple and quick to do a changeover. Now, the guide point or the concept of guide point, it not only is for a single sensor, but it's also for two sensors. It's just a matter of us going into the mathematics of it. It's just simple algebra that we need to go through. But essentially, we can even have a guide point for center guiding applications. And that guide point would be a function of the relative position of the two sensors, and then basically how they are installed with respect to the center of the machine. And then the movement of that guide point would be seen at each of these sensors by half the change in the guide point. So, and when we have two sensors, we can come up with all different scenarios, and we can also offset the web guide from the center line position based on making some changes to these guide points. And like I mentioned, if you don't know the width of the material that you're running, or the product could have variations in width, then if you put two sensors that are equidistant from the middle of the machine, irrespective of the web width change, the guide point need not be changed. So there's really no need to change that. So for example, here, when we change the web width from a wider web to a narrower web, um, the width is going to go down equally on either side of the web. And since the web guide is already controlling it, it's going to make sure that it sees the same amount of web on either sensor. And that helps us to do changeover without even changing the guide point when we use two sensors. So mainly, center guiding offers us several advantages. First and foremost is that it averages the edge position, because we are looking at both the left edge and the right edge, and that helps us averaging that. And when we look at other challenging applications later on, we'll see that how that is helpful. And then you don't need to do any guide point adjustment. And then even with a manual or automatic sensor positioning is not necessary. It's really simple to install, maintain, and operate. And technically, if you have two sensors on either side of the web, it is an inherent web detect sensor, so you don't really need another sensor to say if there's a web is present or not. And then you can also do width monitoring at the same time. Web guiding and width monitoring can be done at the same time with this kind of system. Another concept that that I wanted to introduce is what is called as a deadband. So now the guide point is the reference position where the actuator will change direction to guide the web. You can introduce what we call as a deadband, and what that does is that whenever the web falls within this deadband, the actuator will not actuate. As you can see, this web edge here is kind of like fuzzy and serrated, and it's not that great, while here it's like a straight slit edge. You don't really want the web guide to be moving back and forth for every small change in the web edge position. And in order to avoid that, you can introduce what is called as a deadband. And essentially what it does is it's a region where the error is going to be 0, and then this nonlinearity here, and then the error becomes negative or positive based on the direction. So the deadband is usually around the guide point, and it's usually maybe half a thousands or 10,000s, sorry, 5,000s or 10,000s. And you can also adjust the deadband electronically based on your application. When you don't have a really nice edge, then and you don't really want the web guide to follow those edges all the time, you just want a gross positioning of the web, you can also filter the edge position. Typically, we use like an exponential moving average kind of a thing. So for example, here, this is data from one sensor. As you can see, it's kind of like a sinusoidal position here. And then this blue line here is the data from the other sensor. And the standard deviation is about 7 for each of these sensor outputs. Like I mentioned, center guiding is going to average out that without any filtering, just by center guiding, you're reducing that standard deviation just by taking the average of those two signals. But if you go in and actually filter that, like using a exponential moving average, then you can reduce the standard deviation here. So we use what we call it as an exponential moving average edge filter to make sure that we don't react too much to these edge variations. And essentially, it's like an infinite impulse response filter. And, and the coefficients of these can be adjusted based on the speed, or if you know how much variation you're going to see with the web edge, then you can adjust that. The faster you go, the web itself is filtering those variations for you. Um, but it's mostly effective for sinusoidal or randomly kind of distributed edge positions. Now, in terms of some of the challenging applications or aspects of edge guiding, we'll talk about these few items here one by one. So first one is like a fuzzy edge. So you have an edge like this, which is uh, extremely serrated. Maybe it's coming out from some kind of an extrusion process or things like that. And you really don't care about getting it within 5,000s or something like that, but more about, hey, I want to get it in place because I'm going to do an edge trim here. So if you have a edge guide control system, um, just regular plain Jane one, then you're going to have issues with oscillation. So every time this edge position changes, your web guide is going to oscillate back and forth, back and forth. And then your accuracy of the guiding system is not going to be any better than the edge variation that you see here. So one of the things that you can do to handle a web like this is to obviously do a center guiding, and that will average out the two positions, and then use a deadband and filtering based on um, your conditions here. Now, there might be some occasions where you have an edge that is deliberately like this. It's got like a square wave or a sawtooth wave or some kind of um, a profile that is deliberate for the product. Now, what happens here in this case is that if you have a conventional sensor that is looking at this edge, that profile is going to be like a square wave. And the other thing is that depending upon the duty cycle of the square wave, and depending upon the speed and the sampling rate of the sensor, you might be sampling on the high side all the time, or you might be sampling on the low side all the time, or any combination of those. And whenever the speed changes, it's going to cause the web guide to shift or drift based on the speed changes, which is a function of the profile of the web that you see here. So how do you tackle such a kind of a web? Now, we did temporal filtering, that is time-based filtering. We can also do like space-based filtering or spatial filtering, and use what we call as a bang-bang control to do it. This is an example where you have this web that is kind of serrated, and typically we would install the sensor along the cross machine direction of the web. But in this case, we wanted to take advantage of the way the sensor measures the edge position and the offset within the sensor. So we were able to do what we call as like averaging along the length of the web spatially, and then also have a time-based averaging, and then do a bang bang control. That means like it's, if it goes here, move here, if it goes there, move here, and there's a dead band there. So That's one way of tackling a complicated edge like that. Now, the other common problem that you're going to see with edge guiding is wrinkles. Now, wrinkles in by nature, it's really hard. Uh, the type of the wrinkle, it could be like shear wrinkle with different shapes and forms and things like that. But essentially, what it does is that when the web buckles, the troughs that are created, are going to reduce the width of the web. So if you're just going to guide based on one edge, you might be oscillating back and forth because the wrinkle is going to cause the edge to come in and come out, come in and come out, and things like that. And um, most often, um, you should try to eliminate the wrinkle problem before trying to fix it with guiding. But if you have to fix it with guiding, then obviously center guiding with edge filtering and deadband is something that you should try to use to reduce that issue. Again, first and foremost, we need to try to see if we can eliminate the wrinkle problem. And then if you still can't do that and you still need to have better guiding, then you can add these techniques here and uh, do that. Now, and finally, in terms of material, you're going to come across some porous webs or low basis weight nonwovens with a typical conventional sensor that works based on blocking and unblocking. The porosity changes can actually fool the sensor, and that might cause a pseudo edge movement when in reality the web is not moving at all. And this might cause guide oscillation when the sensor controller gains are high, or like a really sluggish response if the gain is set too low. Overall, like a porous web where the sensor signal goes through, then you're going to have issues with guiding. Now, obviously, if you have a better sensor, then you can do better. And if the sensor is not affected by porosity or opacity, then you wouldn't have that issue at all. But if you don't have that option, then you can certainly do filtering and also do deadband if you have a little bit information about um, your web and the opacity changes. So just to give you an idea, this is, let's say, the web um, edge position from one of the sensors, which is in the blue line here, a dotted blue line, and then the other one from the other sensor. When the signal goes through the sensor and when the porosity or the density changes occurs, and that would be perceived as a web position change at the sensor. Now, if you do center guiding, obviously you can try to eliminate some of those, average out some of those, and then and the filtered one is shown here in solid line. So if you do like a moving average filter, then you can further reduce that and try to eliminate a lot of those oscillations in the web guide because of that. Now, if you add a deadband on top of the moving average, that would actually significantly reduce those edge variations or the perceived edge variations because of the opacity changes. And you can do something like that. So just to give you an idea, like if we look at the standard deviation of each of those sensor values, you have a standard deviation close to 1. If you just do with one edge guiding, without any filtering additional thing, if you just do center guiding, you can significantly reduce that standard deviation. Now, if you apply a moving average filter, you can reduce that even further, and then a deadband can reduce that even further. Again, these application of moving average and deadband, all of those really depends upon what kind of material you have, how much information that you have about what is the expected variation and things like that. So those are material related challenges in guiding. There are also challenges in terms of coordinating. So let's say you have two different layers of web that need to come here and they need to be laminated. Um, and this lamination process, the simplest way is to have two standalone web guides that are guiding the web, and then somehow physically have the sensors of those corresponding web guides exactly at the correct position with respect to each other. And if we do that, then we should be able to laminate these two layers of the web. But usually this is, well, sometimes this could be a challenge because if there's web width variation or some changes and things like that, where you would require some kind of a coordination between these two web guides so that when this layer comes in contact with this layer, they are aligned at a certain location, exactly coincident, or maybe offset a certain distance, whatever it may be, based on your application. And if the sensors needs to be moved for width variations, then that's a problem that can cause issues. You really need to make sure that if you move the sensor a certain distance, this sensor also have to be moved that certain distance. So how do we solve that problem? The old way of doing it is what is called as a mechanical chasing. And in mechanical chasing application, you have a master web that is coming here. And then there's a sensor here that is chasing the web. This is similar to the center guide, um, moving sensor center guide, where that second loop was chasing the web for web width variation. Now just think of that um, system, but take one sensor and put it in on the master web, and take the other sensor and put it on the this follower web. And what it's going to do is this sensor has going to have a control loop that is going to move the linear positioner. In this case, it's going to be in and out of this plane of our monitors here. And it's going to move the positioner so that this chasing sensor will match with the master sensor. When this is moved and this is connected to the guide sensor, this guide sensor is also moving uh, in tandem with the chasing sensor. Essentially, we're changing the guide point of this. And this is called as a mechanical chasing application. So again, this is a system where you have a sensor positioner. So there's an additional actuator required, and it adds complexity depending upon the location where this sensor, this web guide needs to be, and where this is. It could be quite complicated in terms of accomplishing this. But it's been done. It's been done with both electrical, uh, electromechanical, as well as hydraulic actuators. One of the drawbacks here is that when we want to do if these sensors needs to be center sensors, that means that we want to justify the lamination based on the average of two sensors, then this becomes really complicated really quick. What is the modern way of doing it? Is basically to use the feedback from the master sensor and send that as an electronic guide point adjustment for the guide sensor. So in this case, the master sensor is recording the web position of the master web, and whatever the variation that is seeing here is sent as a feed forward signal feed forward signal for the web guide that is following the master web. So the web guide aligns the follower web to a guide point that is adjusted by the master sensor's feedback. So electronically, it's very simple to do, and there's only one control loop here, that is the web guide loop. And then the only added thing is that it's not a fixed guide point reference. Now the reference is a feed forward term that comes from the feedback from this master sensor. We can also do center guiding with this. So you can technically have two master sensors and take the average of those two measurements and take that as the center line position and provide that as a feed forward offset to this edge sensor, which can be single sensor or two sensors. So that's what is called as a chasing application. Now, if you want to do more than two webs, then it gets complicated mechanically. But it has been done in the past. And the way it is done is, again, you have a master web, and then there's a chasing sensor. And this first part of it is exactly like a chasing application. So you have a linear positioner that is the loop is closed based on the chasing sensor's feedback. That moves the linear positioner in and out of the screen. That moves the guide sensor on the top web so that the guide point is adjusted. Now, if you want to follow this position for another layer of web, what you have to do is you have to synchronize this actuator and this actuator. This has been done with hydraulic cylinders as well as electronic actuators, but there is a synchronization. Now you are looking at there is one control system for this web guide. There is one control system for this chasing moving sensor positioner. There's another control system for the slave actuator, and then there's another control system for this web guide. So as you can see, it just gets too complicated too quick. And the main problem with these kind of things is synchronization. This master actuator and the slave actuators may get out of sync with respect to each other in terms of the position. Now that creates more problems than it can solve. A more elegant and a modern way of doing it is, again, using the master sensor position information and use that as a feed forward to another web guide and another web guide. Here, we've just shown two web guides. Technically, you can have multiple web guides and you can still do the same thing. Again, it eliminates wear and tear, simple, inexpensive, and it's expandable. There's really no limit to how many you can do. Now, what are some of the considerations for electronic coordination? First and foremost, we want to make sure that the web position variations seen at the master sensor, we can see all of that. That means that you need to have a sensor wide enough to be able to see that. It really depends upon the application and whether that web guide is whether that web is guided or not. Now, in these examples, I showed like this master web not being guided, but there's no reason why we can't guide this web with another web guide and use the position of the web position from this sensor, which is guiding the web as well, and use that for the master sensor can be used both for control and for also for feed forward signal for all the slave units. Web path links, it would be best if the web path links are the same. This would provide the best results so that you don't have any delay. This is usually not an issue for like steady state errors. But if you have some sinusoidal or non-steady state errors, that's when the web path length needs to be ideal. And then if you can't do that, and if your application is pretty complicated where you need to have you might have sinusoidal variations that you need to match, then what you could do is use a dynamics in the feed forward term, basically compensating for the path length variations. This technique can also be used for some advanced situations where you could use two sensors, one sensor further downstream from the web guide, and use that average of these two sensors with some additional dynamics to control the position of the web much downstream from the existing web guide itself. You still need one web guide right at the exit of the web, one sensor right at the exit of the web guide, and then another sensor can be much further downstream, and you can use some added dynamics and feed forward term to do that. And then with these electronic coordination, you can also use deadband and guide point offset. So if you don't want the web to align exactly on top of each other, you need one web to align at 10 mm and the other web to align at negative 10 mm. You can do all those combination of things with electronic coordination. So that's kind of some of the quick applications of edge guiding. Let me just quickly go over some common errors that we see when we are trying to do edge guiding applications. First and foremost, the most common one is upstream misalignment. So what happens here is that you have a web coming into a web guide with already has an upstream misalignment, and this puts the web guide or the actuator at a non-zero steady state condition. And that means that this web guide is already tilted like this here at a position, and this actually limits further correction in this direction. Um, the web guide might correct in this direction properly because it has enough stroke, but then it may not correct here on this direction. Where do we see it? Let's say you have an unwind roll. If an operator is loading the unwind roll, they're not loading at the right location where these sensors are justified to, either to the center of the machine or to a certain justification with respect to the machine. That's the most common thing that we see. Other places, like let's say you have a blown film line and you have a non-centered bubble, that's another place that you can see there. Now, what it does is basically limits the correction on one side. Now, what is the solution for something like that? If you have a sensor that or a controller that can provide a position feedback, and you can take it into a PLC or anything like that, then that would help you not really correct for this issue, but to use that information to make sure you fix the underlying problem, which is either misaligned unwind roll or to bubble not being in the center. And then we can also provide some kind of an alarm signal when the web reaches a certain, if it reaches the extreme position or not. The other thing is, which is very similar here, instead of the web is coming at the right location, but the sensor is at the wrong location. This happens when we do changeover, and if the operator is not moving the web to the right location, that might happen. And as soon as the web guide is put into automatic, this is going to move the actuator or web guide to one side because the sensor was set for a certain width, and the web width has changed, and that causes the same kind of problem. Again, easiest one of the ways to avoid this is to make sure to use a wider sensor. And if you are doing center guiding, wider sensor, all of these avoids the issue of moving the web. And then you can do an electronic guide point adjustment so that you don't have to worry about repositioning the sensor. And then same alarms when the web position is reaching the extreme position, or an actuator feedback to a PLC or a additional monitoring system would also help. The other thing that we see is that let's say the correction on the web guide is 1 inch, but then the web that is coming into the web guide has got an oscillation way more than 1 inch. Or it could be something like not just the actuator stroke limit, but also the bandwidth. But here I just put it as stroke of the actuator. But again, this is where you need more correction, but you don't have it. Well, the only thing that you can do is actually redesign the web guide. If you remember from our last month's presentation, the correction from a displacement guide is actually a function of this guide span. So if you need larger correction, the guide span needs to be larger. So sometimes it may not be possible for you to do that because of space limitation and things like that. Or the magnitude of disturbance is large enough that you cannot really correct it with one guide, so you might have to use multiple web guides there. So that would be a possible solution. So those are some of the concepts in terms of edge guiding. Now let me just quickly go over to line guiding and quickly cover some of the few other concepts in line guiding as well. So edge guiding is looking at the edge of the web. Anytime you want to look at a feature on the web, you would have to use line guiding or contrast guiding. Why do we want to do that? Maybe the web that you have has got edge variations and you're actually printing on the web. This is the most common example, is line guiding is used in the printing industry, where you have multiple print cylinders and then you want to have multiple the web to be aligned to these printed patterns. It's not typical to see web guide between print units, but then once the printing is done, you go to the next process like converting, like slitting, coating, laminating, anything like that. Now you don't really want to cut or coat at the wrong location, so you would justify it based on the printed pattern, which is the most important thing right now, feature right now. So again, you follow a line or an edge or a pattern on the web, on the surface of the web, not the edge of the web. This is used anytime when there's feature registration is needed. And the pattern doesn't have to be a printed pattern. We have done where the web itself has a shape. So some kind of an extruded plastic, which has got ridges or ribs on the web. And the extruded edges are not really straight, but the ribs on the extrusion are pretty straight. So you want to guide to that, you can do that. And usually a camera or a visual sensor is used to do that. Now the advantage is that you can avoid edge variations. And this is the only way to do registration based on surface features. So if all you care about is making sure that in the subsequent process, that process aligns itself to a pattern on the web rather than the edge of the web, this is the only way to do it. It could be expensive depending upon what you want to do. And it does require teaching or interactions. And most common thing that you see with this as a problem is low contrast features. That means that the feature on the web and the background of the web don't have enough contrast variation that you can pick up that feature properly. Now, in terms of line and contrast guiding, you can actually do a whole bunch of different things, um, because we're not just looking at the edge of the web. You can follow a line and you can say, I want to follow the right edge of the line, or you can follow a left edge of the line. It doesn't even have to be a line. It can be a negative space that you're following, like this white negative space there. Or you can follow a pattern, an edge of the pattern, which is kind of straight. Um, and then you can also follow a middle of the line. So any of those kind of things you can do with line guiding with an appropriate sensor, of course. So one of the common things that you're going to run across when we do line guiding is intermittent lines. So instead of the line being solid, you have gaps in the line. Usually when they print a line, it's solid, but it's an example like this where you have a label, and let's say it's a die cut label, and then the die cut has been removed from the matrix. So you want to follow that edge like that. So again, when you have an intermittent line, the main problem is the sensor can provide you the position information when you are right here, but when you're in the gap, the sensor doesn't know. And one of the things with line guiding is that when you don't see anything, there's no way we would know which direction to move, because the pattern could be on any side. In an edge guiding application, if you don't see a web, then you know you need to go this direction so that you can see the web. And if you see the whole web, then you need to go the other direction so that you don't see the whole web. In edge guiding, we know that, but in line guiding, there's no way of knowing which direction to go if you don't see a line. So this is a problem, and the way to address this problem, there are a couple of techniques to address this problem. One is to get some information about this line itself in terms of how long the line is, how fast the web is moving, so that you can have some kind of a sampling frequency, and then you can build in a timer or a timeout timer, so that you can say that, well, if the web is running for this long and I don't see a pattern for this timeout period, then do something. So you can add something like that. This technique does require knowledge of the pattern, and if the pattern changes, it needs to be programmed, speed, and all those kind of things. A better way of doing that is to have a loss of contrast signal and lock the web when you don't have that signal. So what it means by that is, if the sensor sees this line right here, it's got a signal. When it doesn't see it, it has to go into a special condition called as no contrast condition. And in that condition, the web guide can be locked, and then when the line comes back in, the it'll resume control again. Now, the only drawback with that is if the web moves farther that you are outside the viewing area of the line, then that's a problem. How do you avoid it? Well, you have a wider sensor. If you have a wider sensor, let's say you have a 4-inch sensor, and the web is known to move less than 2 inches, then there's no way you will miss this line in that case. The other thing that we see um, with edge guiding is the loss of focus. That means that you cannot really install the sensor just like what you would do in an edge guiding sensor. The motion of the web guide itself causes plane change, and this could cause focus issues. And the solution is using a backup roller or a dead bar, like what is shown here. So if you have a sensor that is looking at the edge of the web, or surface of the web for that matter, but when the web guides actuate back and forth, this twisting in this span is going to cause the web to go closer and farther away from the sensor. And especially when we are trying to look at a feature, the amount of light coming back, the feature teaching, all of those gets affected because of that plane change. So the solution would be to put a dead bar or an idle roller here, and then you install the sensor so that it's looking at the web on the dead bar. The dead bar is going to stabilize the web itself. Wrap angle above like 5 degrees if it's a dead bar, and if it's a roller, it can be up to 15 degrees, but no more than that. And then again, we follow all the same procedures in terms of how far the sensor can be from the web guide and things like that. So that's a way in which we can stabilize the web. Um, And the thing is that this is not only applicable for line guiding, it's also applicable for edge guiding. Let's say you have a pretty big web guide and it has got a lot of correction, and that correction causes the plane change, a significant plane change. You can put a dead bar right there and then put the sensor before or after. If you have like a small 5-degree wrap, then it doesn't matter if you put it before or after the dead bar, and then that will stabilize the web, and that will make sure that the web doesn't touch the sensor when this rotates back and forth. Couple of quick concepts on other line guiding applications. Now, if you have an unwind roll, how do you install the line guide sensor or a contrast sensor? In the other case, this would have been a free span, just because we need to support the web to avoid the focus issues. There has to be a shifting idler that's installed at the exit of the unwind, and this idler or a dead bar has to move with the unwind, and then the sensor has to be installed so that it can look at the web on the roller, and then this sensor has to be fixed to the machine frame. It cannot move with the carriage. And we do the same thing with rewind. The only difference here is that, again, the sensor has to move with the rewind in this case, and then you can have a fixed idler or a dead bar in this span right before it goes into the rewind. So those are the quick application summaries of an advanced guiding concepts. And just to summarize what we talked about today, our recommendation would be, if at all possible, use center guiding. Center guiding provides or averages the two edge position, so it inherently filters or providing an averaging effect for edge variations. And then especially if you have web width variation, you can avoid some of the common mistakes with improper sensor positioning and things like that. You can also use the two sensors to measure web width. That's an additional signal that you can use for your quality control purposes. If you have some complicated materials where you don't have a straight edge and that is causing problems, you should look into deadband in the controller, and then edge filtering. These are a couple of things that can significantly improve the performance of the guiding system. Obviously, if the sensors are unaffected by the material changes, you're going to avoid a lot of other issues that you would see with conventional sensors. Coordinated control, when you want to do multiple web lamination, it's better accomplished with electronic guide point changes. This prevents any kind of mechanical wear and tear, reduces the complexity of the system, and can provide a good performance when compared to other mechanical systems. And as an additional feedback on your web line itself, we would recommend, if you can get actuator position feedback, that can help. And if you're monitoring that information, that can help identify and prevent any performance issues that may be causing from an upstream process. So best example would be like improperly positioned unwind, or some kind of a steady state shift that is coming from an upstream process, or misaligned roller, or anything like that. In terms of line guiding, the loss of line signal, if you are able to get that, then that would be good, because some of the sensors that are available might not have a wider sensing range. So if you go outside the sensing range and you don't know that you've gone outside the sensing range, then at that point the web is not guided, it's just free floating kind of thing. So if you have a loss of line signal, then you can use that into your PLC and avoid any issues that you might have. That's a quick summary of what we talked about. Again, some additional resources that are available on our website. Feel free to go to our website and take a look at that. And then our contact information. So once again, we really appreciate your time today to um, listen to our presentation, and we'll open up to any question and answers here. Okay, there's a question here that says that shouldn't the rewind sensor position be in the moving station? That is correct. I think that's how we had it here. So the sensor is actually moving with the rewind here, and it's chasing the web. It's not actually guiding the web. If you look at the unwind, it's the opposite. The sensor is actually fixed. It's not very clear here, but it's not attached to the carriage. The sensor is fixed, and then and that's how it is. Okay. Okay, is there a reliable web sensor for high temperature, 200 degrees C for clear films? I am not aware of anything. Our sensors are rated for 85C, and they can work with clear films. Most often clear films, ultrasonic sensors are used, but at 200C, the frequency of the crystal would be affected by it. So we might have to get back to you on that if we know of any sensor that can be used at 200C. There are some other questions that are specific to our product, which we will answer separately. In a winder application where the entire winder is on a shifting base, where is the idle sensor placement in the machine? At the winder inlet, idler, or further downstream, or close to the actual winding location? Okay, so that's a great question. Let's see. So ideally, in this winder or rewind, it's kind of the same thing here. Ideally, we want to put this as close to the winder as possible. That would be the ideal location. If you have a roller that is going to take care of the diameter variations, then putting this sensor as close as possible here would be the ideal location. Farther away, again, we're adding delay to the system. There's another thing that is not considered or not talked about enough, is that the stiffness of this mechanical arm that is holding this sensor is an important factor. If the arm is not stiff enough, that's going to cause winder instability. So as you put it farther away, the stiffness or you got to make it really beefier to be able to have a stiff sensor there. So ideally, as close to the binder as possible is the ideal location. Okay, are there other filtering methods besides exponential moving average that might be more optimal? Um, Exponential moving average, the choice of that is mainly because of the fact that it is easy to implement. It's a pretty simple filter factor. That's the reason why it's more popular. Let me see if Carlo has any other comments about that. But to me, exponential moving average is the most simplest one and easiest one for us to implement. This is just purely for filtering the edge position. Obviously, you can have some advanced control system where it has a filter built into the controller itself, like an adaptive control or things like that. So there's a question about upgrading to wider sensor. Uh, yes, it's possible. We can upgrade it to uh, any of the wider sensors. Okay, any other questions or comments? Okay, hopefully you had a chance to take this poll and um, just to give you an idea. Okay, so a wide group of people, mostly in converting, and then also in terms of job titles, um, operations, maintenance, plant engineer, and then design engineering and R&D are kind of the key areas here. Okay, so if there are no other questions, we will conclude this webinar. Um, we will also follow up with people who ask questions in case they have any additional clarification. And we will continue the series with another webinar next month. And we have collected some feedback from attendees about what would be the ideal topic. And based on that, we're going to have the next month's webinar. We really appreciate your time to join us for this webinar. This webinar will be recorded and we should be able to post that on our website within the next few days. And we look forward to seeing you next month. Thank you so much. Have a great day.